Good morning, everyone. How is everybody today? Hopefully you're doing well. Cool. Sound is working? Sound is working. Cool. So, hi everyone. Hope everybody's doing well today. Yeah, nothing really to report today. So, we'll just jump right into our lecture topic for today. Since we, we need to make up some time, so the only way to do that is to get right down to it. So, although normally I try to be a slight bit courteous and allow, the people who aren't here right at 9:30 to be, in the stream. However, since this is the YouTubes, if they want to see the whole thing, they can just, rewind it by 30 seconds or whatever. But yeah. Cool. All right. So, last time, on Tuesday, we finished off talking about default parameters. So, default parameters in Python, just very briefly, these are parameters that are optional to provide, so you don't have to provide them. If you do not provide them, then the default value which is specified will be substituted. So, in a very simple example, if you have add x, y, and then z with a default parameter of 3, and then return x plus y plus z, you can say add 1, 2, 3, or that one. Let's do something different. 4, 5, 6 is 15. 4, 5 is 12. Because the 6 becomes a 3 because it's the default parameter. There are lots of functions that are there are lots of parameters, or there are lots of library functions that have these types of default parameters. Like, for example, the print function. If you take a look at the help for the print function, incidentally, this is how you get documentation on functions, if you didn't know that already. We've got things like separator and end, and what you want to write it to, and whether you want to flush it. All of these are things that you can provide optionally. So, one might say, then, how does one go about providing an optional parameter if it's not in order? Because, of course, for this one, it's like it's in order, right? You don't have to do anything special to get at the z, because z is the only one, and, it's in order, etc., etc. So, if you want, you can say, you can specify the name of a optional parameter from a list of optional parameters by picking it out particularly and doing like a quasi-assignment statement within the function call. So if we do that, notice that it says hello world. And notice also that it does not do the usual print thing of providing a new line statement at the end of that print operation. It just immediately jumps into the command prompt for the next operation. Why might it be doing that? Well, if we go back into the print, notice that the default value for end, which is the thing that's put on the end of the thing you're printing, is new line, the new line character. So that's actually what we're doing there, is we're actually reconfiguring that. We're overwriting the new line that is normally and typically provided with this world. If you want to put it back in, then it's easy enough to put it back in. But, you know, anyway, that's default parameters. Can you... Yeah, I'm pretty sure my voice is working. Yep, I'm good. The problem is you. Say that as nicely as possible, of course. So let's talk about scoping. We've touched on scoping briefly over the course of the course, but let's drill down some of those details. So what do we mean when we're talking about scoping? The scope of something in a program, you can think of that as the territory in which it exists. It's like, think of it like countries, right? If you're in Germany, the laws of Germany apply. If you're in Switzerland, the laws of Switzerland apply. The laws of Switzerland do not apply in Germany, and the laws of Germany do not apply in Switzerland. So you can think of the laws as being scoped to the countries. It's kind of similar to that. And I know they're all part of the EU, so they basically share a common legal framework at this point in time. Think of that example as being more relevant in the Renaissance. But anyway, or at least pre-European Union. Not to get into politics or anything, but, or history of politics. Anyway, so the idea of a scoping is you have a variable, and it exists within certain contexts, and it does not exist within other contexts. So, generally speaking, we recognize a distinction between global and local variables. This is kind of a little bit, this is kind of like one of those chemistry analogies that gets more and more complicated the more you learn about chemistry, because this is kind of a rough approximation of how things work without actually, it's not necessarily exactly how things work. How things actually work is that you have degrees of locality, and something that's global in one context, like if you have a variable that's global within the context of a particular Python file that you've written, a Python program, it is local to that program, but, global within the context of that program, but local to that program within the context of the operating system, for instance. So, and, processes in the operating system have greater or less locality depending on how close they are to the kernel, essentially. So, but within the context of a single Python file, all you really have to worry about is global and local. Global means it is available everywhere. So, extending our legal framework analogy, global variables are something like maritime laws. So they apply regardless of nationality, and well, it's also it doesn't quite work because maritime laws don't apply unless you're like in the sea. but something like a universal, like the UN's Declaration on Human Rights, right? Ostensibly, every country should theoretically follow that, as long as, they're members of the UN and whatnot. But, it's a thing that applies everywhere. Whereas local variables apply only within the context that they're defined in. And this is normally functions, but it can also be classes. So, I hate when I do that. Ugh. Alright, so let's consider the following situation, the following program. We have an n declared, we have an x declared, we have a for loop, and then we print. So, within a Python file, you can consider a variable to be scoped to every line after it's been declared, right? So, the first use of a variable in Python is implicitly the point of its declaration, and that variable can be thought to exist at every point past its declaration within its context, right? But we'll get into it. So in this particular example, everything is happening within main execution, which is to say not inside of a function. There. So these variables, n and x, are being declared in the so-called global context. All of these variables are global variables. So global variables are okay, but there are some reasonably strong problems with global variables that sort of come into software design and how to design software so as not to kill yourself later, or make you want to kill yourself later because of how terribly the software you've written is, and how, how you now have to use this software that was written so terribly. Believe me, this does happen. The problem with global variables in general is they sort of cut against the principle of modularity. So when you design things to be modular, you want to design a thing like Legos, right? Legos are a modular system. When you take Legos and you stick them together and build something big out of little tiny bricks, the whole thing about a Lego is that you do not need to know very much about, the individual bricks do not contain any information about the structure as a whole, right? It's the fitting together of the bricks that constitutes the larger structure. Ideally speaking, you want to configure your software along roughly those lines, except the difference being when you're playing with Legos, all of the Legos come to you. You buy Legos, right? In a computing context, you have to design the Lego bricks yourself a lot of the time, and if you're not designing the Lego bricks yourself, you're using library functions that are composed of Lego bricks. And the other difference is that between software and Legos is if you want 500 eight knob Legos, you have to buy that many 8-knob Legos, whereas with software, everything is infinitely reproducible by copy-paste, right? The fact that these things are reproducible is baked into the structure of the programming language itself. You don't have to buy 500 copies of the particular module that you need for this particular part of the thing. Well, at any rate. The analogy starts to break down, but I think it's a pretty good one. Yeah. And the other, going back to the Lego analogy, you only have to understand how to put together, you don't have to understand a huge number of operations to build something out of Lego. That's why it's an ideal an ideal toy for children, right? Is because a child, like a 5-year-old, isn't going to write God of War the video game, right? Because they haven't reached that level of cognitive complexity. But they like, because Legos operate on a very small number of rules, they can play with Legos and do interesting things with them. Emergent design out of very simple rules. Software ideally constructed has similar properties, but in order for it to have similar properties, you have to design it with modularity in mind. And the global variables, again, cut against that idea, because when you use global variables, it means that the global variables are going to be the same each time. Every time we run this piece of software, n is going to be 7, x is going to be 1. If, however, we encapsulate this piece of code that we want to execute inside of a function, then we can parameterize n and x, and we can run this code for any value of n or x. This increases the utility of this piece of code by many orders of magnitude. Let me see if I haven't lost everybody. So, comparing the global context to a local context. Functions are kind of your touchstone for the easiest. This is like your basic, most basic form of what a local variable is. So, within the context of the function, the parameters of that function are scoped to that function, right? Any variable that is declared within that function is scoped to that function. So it does not exist outside of that function. So, for example, if I had a function, actually, we've already got add defined, right? So it doesn't have any variables declared inside of it, but variables and parameters are basically the same thing in Python, so you don't have to worry too much about it. So I have, in this step here, 4 was assigned to the value of x, right? So what is x? X is undefined. That's because when the particular running instance of that function is finished, all of the variables that are contained by that function cease to be. They are deleted. If you want to know how the computer actually works, hold on to your butts, because this is going to get a little technical. So this is how your computer actually works. Inside of your computer, there is a memory structure called the call stack, right? So, you know Stack Overflow? Some of you may have used Stack Overflow, right? Popular website for answering questions about programming issues. The stack referred to by Stack Overflow is the system stack. Stack Overflow is a notoriously difficult to find error that can sometimes happen if you exhaust the size of that memory structure in your particular computer, which normally only happens if you've bungled a recursion or something like that, in the modern context at least. Back when memory was much more expensive and limited, Stack Overflow was the sort of thing that you would see a lot. So, you know, I remember on my old Windows 95 machine, I nearly crashed a thing once by opening 10 instances of Solitaire. You know? But anyway, so the system stack. The system stack contains all of the functions that are currently being executed by your computer. So imagine we have a function that calls a function, right? Let's say we had function A that calls function B, and all of that is being run inside of a Python program, right? The Python program has what's called a stack frame. So the stack frame contains things such as the specific commands that are sent to the CPU to be executed, the memory that the local variables are made up of, or local to that context. So in this case, we would be talking about the global variables and various other definitions and things. If you take a look at Python Tutor, Python Tutor, they actually show you this explicitly, which is kind of cool. So let's say we had a def b, it takes x, return 2 times x, def a, y, return b, or let's say q is equal to b times y, and r is equal to b times 3. I'm just making up sort of a facile example. 3 times y. There we go. Return q plus r. Right? Just some functions. And then we want to print a at 7. Something like that, right? Visualize execution. So first, within the global frame, we've got a function definition for b, because it's declared first. Then we have a function declaration for a. So these function definitions are within, well, because this is an object-oriented programming language, they're considered objects, right? Because everything is an object and object-oriented. But it's sufficient to think that within the global frame, these two functions have been defined. So when we print A7, the first thing we do is we open up an instance of A. So when you execute a function, what you're doing is you're taking the code and all of the variables and all of the everything that constitute that function, and you're putting that on top of the stack. So the stack is kind of like a stack of plates, right? It's like the last thing on is the first thing off kind of idea. So A is placed on top of the stack. A is that now the top of the stack, and the top of the stack is always whatever function is currently being executed. But this is how the computer is able to jump into functions while maintaining its memory about the thing that called the function. Believe it or not, at a certain point in computer history, this was a huge innovation. Absolutely huge. So it goes through, it declares, so it goes through, it tries to execute this statement. It's like, okay, this contains an instance of the function b being run. So it opens up a new frame, right? It opens up a new frame for the function b, and now it's going to execute b. So it executes b, its return value is 14. 14 is going to get returned back to the a frame, right? There we go. Q acquires the value that's returned by the b frame. But notice that b, the b frame here, is deleted along with everything it contained. So b no longer exists. Any variables that were inside of here, like the x, those no longer exist anywhere inside of the stack frames currently existing for this program. It's done. Everything is deallocated and deleted. And if b is executed again, we place it on the stack again, we execute whatever it needs to be executed inside of it, its return value is found, that return value is returned to the... So it's kind of funny, because like the way things work is a return value is always being put down one level on the stack to whatever the thing was that called the thing that's returning the value. So now that we've hit now that we've hit the return statement of the A frame, we find the return value of the A frame, and bada bing, bada boom, the A frame is also removed from the stack, and the output is returned. So there we go. So that's how your computer actually works. And that's why a variable outside of the local context doesn't exist. That's the reason. So, yeah. I'm going to see if there are any questions about that. Civ Gandhi stack overflow glitch. That was integer overflow, not stack overflow. That's a different type of overflow. So, I'll explain that one very briefly. So, imagine you have, let's imagine you have a 4-bit integer, right? 1, 1, 1, 1. Let's say that the 4-bit integer has the maximum value of a 4-bit integer. That means the bits are 1, 1, 1, and 1. What happens if you add 1 to that? It becomes 0, 0, 0, 0. That's how the circuits work, actually, underlying, like, all of the calculations. So it's not so much a problem anymore, because modern programming languages sort of guard against these types of errors. But if you're programming in C, for example, integer overflow or underflow, because it can happen in the reverse direction as well, the famous example is in the Civilization games. Gandhi, the leader Gandhi, has the lowest level of aggression possible, and aggression is stored inside of an integer. So, it's like, by trading well with Gandhi, you can actually reduce, you can have an effect in-game on the aggression level of the other computer-controlled players. Like, if you do favorable trade deals with them, you can get, like, you know, attitude points, and those attitude points can contribute negatively to the aggression. So if your aggression is already at 0, and you subtract 1 from that, then the aggression will underflow and become the maximum level of aggression. That's why in the Civilization games, if you were nice to Gandhi throughout the game, by the time he hits the ability to have nuclear weapons, basically he just builds up all of his nuclear weapons and annihilates the entire board and, like, just destroys everyone because he's been underflowed into the maximum aggressiveness. The maximum possible aggressiveness, which is, you know, within the context of a Civilization game, that means trigger-happy nuclear holocaust. So there you go. Yes, no, the other Gandhi, the famous one who gets into the Civilization games. Yes. Anyway, so yeah. So not going to belabor the point too much, but because we use a function, and this function can be run for hypothetically any factorial number that we wish to calculate, so long as it's sufficiently small, because factorial blows up so quickly. You know, this is modular design. As I've already kind of demonstrated this, if we attempt to print variables that are internal to a function declaration, that results in a, name x is not defined error. So, how do we get around this? How is it possible to use a global variable within a local context? Because it is possible. So the thing that you have to do in Python, basically the way that it works is you have to give yourself read privileges. So let's take this example and do something with it. So print that so that we actually run things, and print let's say, Q inside of A. So if we run this, of course, we're going to hit a error Q is not defined, right? Sure. So let's declare Q up front, right? Let's declare it within the global context. Will this work? Let's see. You just fixed... Get out of here. So, boop, boop, boop. Q has been declared. See, it's right there. Boop, 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 boop. Uh-oh. Uh-oh, look at that. We have double Qs. So this is what the default functionality is within... And this isn't just Python. A lot of different programming languages do this. So if a variable is declared within a local context that has the same name as a variable in the global context, they won't actually interfere with each other. This Q is distinct from this Q here. Notice that they're, at this point in time, holding different values. They are distinct segments of memory. So, it doesn't... So you've got a Q in the local context, and you've got a Q in the global context. And whenever you use a variable like Q, the computer will always assume that you mean the most local context possible, unless you've specified otherwise. So how do we specify otherwise? How do we say to the A function, listen, I actually want you to use the global variable Q? Well, you have to declare it global. Get out of here. There we go. Live programming. No. Visualize execution. There we go. So, we've got Q is 0. Right? It skips this, but essentially, check that out. So, once B is finished, where it puts the return value is in the global Q. So, by using this line here, global Q, this declares Q as being tied to the global instance rather than the local instance. So you notice a local instance of Q is not even produced. We get an R, but not a Q, because we're using the instance here. So that's how you would access global variables within Python functions. You have to give yourself explicit permission to use global variables. In general, it's not a recommended method. You should know how to do it, but generally speaking, what you don't like, this is not a technique that you're going to be using a lot if you're a good programmer. Yeah. So, yeah, cool. Yes. So, yeah, yeah. And these slides basically say the same thing, but with a different example. So, one of the reasons that we don't like global variables is because, generally speaking, we try to avoid what are called side effects. So, it's like one of the Zen principles of programming, one of the mantras of programming. Same input, same output. Same input, same output. Essentially, you want to design your program such that if this program receives the same input, it will produce the same output. That is to say, if you feed it the same input multiple times, it should produce an identical output value for each time that it's run. This is actually a principle that's been baked into the manner in which the assignments have been designed, right? We assume that you're writing your functions in such a manner that if we run your code with particular inputs and you run your code with particular inputs, both times the code is run, the particular and expected output will be produced. That's baked into the idea of the assignments themselves. So the problem with global variables is that if you're using global variables within the context of functions, those global variables might change, outside of the function, right? It's like, imagine going back to our Python tutor example. Let's modify this slightly. Let's say that we did q plus equals b, like this is it, right? Now let's say we run the thing a couple of times, right? So on the first run through, the output that we get is 56, right? And the q value is 14. On the next run through, the output will be 70, and the q value is 28, right? And the third time we run it through, we get 84 and 42. Now, obviously, there are situations in which this could be useful. There are always going to be situations in which all of these little, bits and bobs, basically, and this actually used to happen a lot in the 80s, before a lot of the sort of ways to not hurt yourself coding were established. If there is some little semantic thing that a computer does, a computer nerd is going to find out a way to turn that to his advantage. So there are definitely ways in which this can be beneficial. Nothing is a universal poison, right? However, this directly contradicts the idea that a function should always return the same output when given the same input. And, this can be a complicated thing to, in this case, all of these print statements are obvious because they're all in a row, right? But if you've got several lines of execution going through a very complicated program, it might not be obvious to you when and in what order the functions are being called, right? So, there's that portion of it. There's also the portion of it that, generally speaking, you don't want to have requirements on the calling of functions other than the calling of the function itself, right? So, it's like a design principle that you want to minimize the amount of code that's necessary to correctly run the function to the invocation of the function itself. In this particular case, q has to be declared and initialized to whatever you want it to be initialized to prior to the calling of A7. Now, it doesn't matter how good your documentation is, that's not a great way to design code. It's the same thing with return values. So, if your function has been written such that the return value is, false if the inputs are invalid, whoever's using your function then has to manually check if the function is returning false or if it's returning a non-false value, and then use that value accordingly, right? That means that whoever's using your function, which might be you and it might not be you, they have to be checking the results of your function using if statements. They have to add code to their code to make up for the fact that your code hasn't been written exactly properly. But so anyway, you want to try to minimize the amount of code required to run a function to the invocation of the function itself. And global variables, again, cut against that idea. Good. Cool. All right. Questions? Bloop. Would returning q with the function also allow q to be a global variable along with the desired answer? I mean, well, one of the things about this is that you don't have to, if Q has been declared globally, then you don't have to return it explicitly, right? Any global variable to a function is implicitly a return value of that function as well, right? That's another way of thinking about it. It's like I can access what the value of Q was after the execution of the function. It's not the value that the function call is being substituted with, but you can get at its value post fact, if that makes sense. Cool. So let's talk some software design principles. Maybe we can bang this section out in 12 minutes. Let's see. So, I've already been talking a lot about these types of things today, so this should be just a sort of recapitulation. Hammer things home. So, modularity/decomposition. A program is broken into parts or functions that are A, reasonably self-contained, B, achieve a clear purpose, and C, can be reused. So, think of your program as being made out of Legos. Legos. A Lego brick is self-contained. It has a clear purpose, and it can be reused. Programs are Legos. This is going to... I'm assuming everybody in the class has at least seen Legos or knows what Legos are. I am, in some sense, trading on the cultural ubiquity of Lego at this particular instance, but hopefully that's a reasonable assumption. Anybody in the chat not know what a Lego is? That would be interesting. I'm always interested to see if the things I consider to be culturally ubiquitous actually are. Because at this point, you have to worry about cultural ubiquity on a global basis. Anyway. Yeah, actually. Lego. Lego. Yeah, but okay, but pictures of Lego. Yeah, these are Lego, right? These little plastic bricks. You can make stuff out of them, right? All kinds of fun stuff. You can bake basically anything out of Lego. But anyway, yeah. Cool. So, yes. So, by making our functions modular and composable, we are actually performing a type of abstraction. So, when you deal with a Lego brick, you don't, you're not interested in, the precise, construction of the Lego brick. You don't really have to care about how all those, tines on the inside of the underside of the Lego brick actually hold the pieces together. All you have to worry about is if you push the pieces together, they stick together, and then you can build stuff with them, right? Your mental model for a Lego brick is much less complicated than the physical reality of the Lego brick, right? This is actually a good thing. This is how the human brain works. We do not, generally speaking, work with, physically accurate representations of objects in our brains. I do not think about this cup. The diameter at this point is this much. The diameter at that point is this much. It has this degree of taper. The fluid that it's filled with is composed of this chemical, that chemical, that chemical, that chemical. We don't deal with things at that level. We deal with things at the level of cup, tea, good drink, right? Drink tea, good. Tea, drink, good, yum. That is the level at which your brain operates, right? It's like ruler for measuring, measure with ruler, right? You want to write software that can be used in accordance with that type of a principle. When you use the sine function, it's not important, sine as in like the trigonometric function. It's not important to know how sine is being calculated. It's not like whether it's a giant series of formulas or they're just using a lookup table or something. It doesn't actually matter, right? All that matters is that if you put a number in, you get the sine of that number according to trigonometry, right? Or whatever reasonable approximation we can come up with for it according to floating point arithmetic. So this is abstraction. You want to be able to deal with pieces of code in an abstract manner. You don't need to know the details of it. You just need to be able to know, how it's used and what it produces, right? That's how you want to deal with software. Of course, the difference with software is that it is kind of this completely and wholly artificial construct, right? So, in software, it's interesting because you actually get to decide what level of abstraction you're dealing with, which is not the case in most of physical reality, right? In physical reality, your brain takes care of that for you, and if it doesn't, then you have a serious mental problem because, if like it's super, super easy to get overwhelmed by the detail of life, right? You can imagine a person who didn't see a snowbank but saw every snowflake in the snowbank. They would go mad from just the sheer volume of detail. Your brain wouldn't be able to handle it. The abstraction is necessary. But in software, we get to decide what level that abstraction operates at. And generally speaking, more abstraction is better so long as the abstraction principle holds. And in software, the abstraction principle holds so long as you're writing your functions in a manner that is modular and decomposable/composable. There we go. So this is particularly the case. You particularly want high levels of abstraction going on if the size of the problem, size of the functions that you're dealing with, or the size of the programs you're dealing with are large. Right? The larger the problem is, or the larger that the program is, the more abstraction you wish to introduce to try to cut down some of that extreme complexity. At a certain level, all software development devolves into complexity management, right? Software is actually the most complicated thing on the planet aside from the human brain. So, these abstraction mechanisms are absolutely essential if you want to operate on a software program of any degree of complexity. The assignment functions that we've been doing in the course so far, these are very, very uncomplicated programs, relatively speaking. Like, there's a reason they're math problems, these things are math problems and not projects, right? But anyway, each function within a larger thing, a larger software entity, should do one thing. You should be able to look at each function in your program and say, you have one job. For example, Twitter, storing a new tweet in the tweet database, because that's what Twitter is. Twitter is a database, and that's it. There's like one function that stores a tweet, and all that function does is store a tweet. There's one function that records a liking of a tweet. It is wired to a button. When you press that button, all that happens is a tweet is liked. Whether or not there are larger implications regarding discoverability and all of that sort of thing that are related to the data that's collected by the liking of tweets, that's a separate function, right? The actual liking of the tweet itself is one function. Everything else is further downstream, other functions that are downstream of the data that's input by the liking or the disliking, etc., etc., etc. So, Cool. Let me see if we got any questions. Team T? Oh no, I do have coffee. I just have my coffee with breakfast. That's all. No, it's green tea in the morning, black tea in the afternoon, herbal tea in the evening. You have to be careful to manage when you get to start getting to like around my age. You have to start being careful about your managing your caffeine consumption. If you delete the tweet, could the function be recalled back so that the software saves some space in the database? If you delete the tweet, could the function... I guess the question is, like, is deleting a tweet basically the same thing as adding a tweet? Just run in reverse. So, generally speaking, in software, like, at the level we're talking about it, you should get away from the idea that there's an undo function. Generally speaking, in, like, Word or, Excel or some sort of other, software program that has an undo function, that only exists because somebody programmed it, right? And, so I'm not sure I completely understand your question, but yeah, generally speaking, when something is deleted from a database, that makes the database smaller, right? It depends on the manner in which the database is stored, but yeah. Anyway. So, oh my goodness. It's 10:19. We'll talk about documentation next week. Boom! Alright. Cool. My cam froze? Oh, yeah. Happens all the time. At least it's a not as stupid looking a face this time. I don't know. It's like it always gives me like 50 minutes and then it does that. I don't know what it's doing. Yeah, it also switched it switched me off my good mic as well. What's even the point? What is even the point of view? Boop. There we go. Cool. All right. Would returning Q with the function also allow Q to be a global variable along with the desired answer? Oh, yeah, you could do that. Did I close Python Tutor? I did. Oh, man. Yeah. Yeah, if you wanted to, you could make Q the explicit return value. So the difference would be when you return Q, it would take the value that is stored in Q, make that the explicit return value, which is stored separately in memory, and then put that in where that would become the replacement for the function call in whatever expression you called it in. Yes. Yeah. Hopefully that's a decent answer to your question. Cool. Any more questions? I suppose if you have questions, then you could just jump into my office hours. Office hours are happening quite soon. So, in a matter of 10 minutes on Teams. So, I guess I'm going to log off here, If you have any questions for me, you'll know where to find me. It'll be on Microsoft Teams. Stay frosty, my friends. Etc., etc. Sign off saying, etc. Whatever. Take her easy, folks.